Welcome to this explainer. Look, if the grade 12 math syllabus feels like this massive, overwhelming mountain of formulas and theorems, it really helps to reframe it. Today we're taking chapters 1 through 5 and transforming them into your ultimate empowering survival toolkit. We aren't just going to blindly memorize equations here, we're going to actually understand how to wield them.
Okay, let's dive into this. Here is the 5-part toolkit we are unlocking today. Complex numbers, proving with mathematical induction, mapping 3D solid geometry, navigating vector algebra, and finally, permutations and combinations.
All right, tool number 1, unlocking complex numbers.
So how exactly do we solve impossible problems? I mean, for years, finding the square root of a negative number was basically considered a mathematical dead end. But then, enter the imaginary unit, I. This little letter is a total game changer. By mathematically defining I as the square root of -1, which means I squared equals -1, we literally unlock solutions to equations that used to stop us dead in our tracks. Take a classic roadblock, like x squared equals -4. With our new tool, we don't just throw up our hands and write no real solution. No way. We can confidently say x equals plus or minus 2i. Just like that, the impossible is totally solvable.
Now, what's really interesting here is that we can actually view these numbers in two completely distinct ways. On one hand, we've got the algebraic form, z equals x plus y. You could think of it kind of like a standard city map using an x and y grid. But if you shift over to the trigonometric or polar form, instead of walking, blocks east and north, we measure a direct, straight-line distance, r, and an angle of rotation, theta. It's exactly the same number mapped out, just viewed through a completely different, and honestly often way more efficient, geometric lens.
Moving right along to tool 2, proving with mathematical induction.
All right, we're shifting gears now from just calculating numbers to establishing absolute, undeniable proof. It's like setting off an infinite chain reaction. First up is the initial step. You prove the statement holds true for the very first case, where n equals 1. Think of this as flicking that very first domino. Second, the inductive hypothesis. You assume it's true for an arbitrary case. Let's call it n equals k. And finally, the conclusion. Using that exact assumption, you logically prove it absolutely must be true for the very next case, n equals k plus 1. Look, if the first domino falls, and any falling domino guarantees the one right next to it will fall too, well, you've just proven that the entire infinite line of dominoes is going to topple. It's honestly such an elegant way to prove a formula works forever.
Okay, tool 3, mapping 3D solid geometry. It is officially time to step out of those flat 2D planes we're so used to. You know how when we worked with an x and y axis, the world was neatly